Bruno Fernandez-Ruiz. Actually, let me pause. I'm gonna tell my wife to turn off the radio. I have a very All right, sound engineer Brian, sorry about that. Now we are back. All right, from the top. Bruno Fernandez-Ruiz, CTO and co-founder of Nexar Inc. Welcome to the Data Exchange Podcast.
Thank you, Ben. It's great to be back.
So Bruno, today we're going to talk mainly about edge computing and related topics, but to put yourself in perspective, for our audience, briefly describe Nexar. What does Nexar do?
Nexar, it's essentially think about air traffic control, but for the road. So what we have is hundreds of thousands, millions of vehicles with cameras, and what you see helps me in real time to drive, and what I see helps you in real time to drive. It's collective intelligence, crowdsourced intelligence, vision-based for the road.
And what is the data collection mechanism?
So what we do is essentially we run a variety of AI models at the edge, hence the topic, and this helps us find interesting data, relevant data, events, detections, classifications, move sometimes just the metadata, sometimes also the raw footage to the cloud, to AWS, to the region, and then broadcast that back to the vehicles and aggregate it eventually for other purposes of reporting statistical patterns and where things are to things like cities or people who are interested to know where are the construction zones happening today, or what are the road signs on the road, and what is that 50 speed limit that just changed.
All right, so let's go to edge computing. So I don't actually know when historically this term was introduced, but in your mind, what are the things that fall under the umbrella of edge computing?
Yeah, so there's obviously, I think there is one that everybody would agree, right, which is embedded devices that had certain level of connectivity to a network are part of that edge, and that's really what it ends, right? That's the terminal device that you're talking to is the edge. Beyond that, there is no internet, there's no connectivity, so that's beyond the edge. And now what some people, including ourselves, have started to talk that, well, you have that device and the device that talks to. So where the telecommunications network ends, that's also the mobile edge, and then you have the actual consumer device edge. So the way we phrase it is provider edge versus consumer edge. So provider edge, I'm a telco, I have a data center very close in the metropolitan area. That's where it ends. And then as a consumer, I have a mobile phone, or I have a car. That's my provider edge. And some people have called it also fog computing and all different words, but they tend to be basically the same.
So Bruno, I'm going to read out to you the sentence from Wikipedia and tell me what you think about it. Right? So edge computing is a distributed computing paradigm that brings computation and data storage closer to the location where it is needed to improve response times and save bandwidth. So in my mind, as I read that, and actually some people have told me this too, and actually a lot of these things obviously is subjective, right? So, but edge computing in some contexts might even include a laptop, because imagine in a factory, you have computer vision models deployed, but then you may bring a laptop to the factory floor to tweak the model. something like that. But anyway, so I think the elements there are. So you mentioned actually in your definition that it has to be connected to the internet or some network, right?
To a network, yeah. It's the network, it's the edge of the network at the end of the day. So I think that what the definition really comes to that, I totally agree, right? Which is the main issue that happens with edge computing is either you have data and you don't have compute abilities, or you have compute abilities back on the core of the internet, but you don't have the data. And there is this mismatch that happens. And what edge computing does is says, okay, how can I bring, rather than bring the data to the core of the internet, which is unaffordable and impossible based on the design of the internet that is asymmetric, can I bring some of that compute to the edge? That really is the secret of edge computing. So in some cases, that's because you cannot afford to transfer elsewhere from the edge because it's too slow and it's a real-time application. Sometimes it's I can't afford to transfer elsewhere because it's too costly. It's too much data to transfer. So in both cases, edge computing comes into place, which I think really is what the Wikipedia definition you read is getting to.
So you made a distinction between provider and consumer edge. So how different are the challenges for those two?
They share some similarities, surprisingly. So we work both, helping bring in to the telco stack to what's called the multi-edge access compute. It used to be called mobile edge compute, MEC. I think is the general word that you would use. So, in the consumer land, what you find is that, you have all these embedded architectures where you're trying to really do all these techniques of porting, using tools like Apache TVM, right, or OctoML, for example, pushing them, porting the architectures, pruning the architectures, quantizing the architectures all the way down to an 8-bit, looking at which layers and which operators are supported. And that's on the consumer edge to really leverage the wattage, the power, the heating, all these constraints that you have on your chip. Now, when you go to the provider edge, surprisingly, people think, well, that should be like a region in AWS, and it's not, right? This is prime real estate. You cannot end up with these huge data centers in the middle of San Francisco. So what you have is relatively high compute density, not a lot of it, but a very high compute density, but very low storage. And is designed really to address mostly the low latency use case today, and towards 5G start to address the high bandwidth use case, right? That 5G should really not be about just people streaming Netflix on 4K, but also the ability to now shift. So on the provider edge, what you find is that all that optimization that you have done on the consumer edge, on the consumer device, it actually makes sense to use exactly the same techniques on the provider edge, because you want to squeeze in that prime real estate every watt of power you want to extract of it as much as you can, because it's super costly, and you want to really get the return on your money.
So Bruno, for those of us who are not familiar with these implementation. So if the provider edge is not a data center, so in San Francisco, if there are provider edges, what would they look like? Would they just be?
It is a data center. I think it's just, so you could have a building with 2 floors, right? So there will be one floor, like AWS wavelength, right? There will be one floor that is full of racks from Verizon or AT&T, and right underneath, there is another floor that has racks with servers from AWS. And between them, there is a private link VPN that connects the 2 data centers, to call them something. But they're smaller, right? And they have to be closely located for the metropolitan area. So, it's not in the middle of San Francisco. I'm exaggerating, but, every metro area and both, GCP, Azure, and AWS are going to that strategy to bring more of their core technologies onto the edge to enable these type of applications.
So instead of football field size data centers, they could be a floor in a city, but then there'll be several buildings with these edge provider edge.
Yeah, I mean they're normally in the suburbs of the city.
Okay.
You can afford a millisecond of electricity travel, light speed, and they tend to be a little bit bigger than just the floor. But conceptually, yeah, that's exactly what is happening. Right? So rather than having these huge factories or chicken coop hectares, what you have is essentially a relatively mid-size factory with servers right on the suburbs where you would expect other things to be.
So let's go to, so just to make this even more concrete. So let's have you rattle off a few prototypical use cases of edge computing. So there's the stuff that you folks do, which is basically putting AI in computer vision on dash cams. So kind of that mobile device kind of example. So when people talk about edge computing, sometimes they talk about appliances. I don't know how real those
Yeah.
are. Definitely factories, right?
Yeah, so I think the pattern it goes back to the same, right? Is this edge computing makes sense where you have way too much data somewhere that you cannot afford to transfer either because of latency or because of bandwidth. So if somebody says, I don't know, a fitness device or a temperature sensor that triggers once a minute, you go like, well, no, right? Just transfer that data to the internet. It's not a lot of data. If you have an engine that is generating 50,000 points a second, well, now you have a bit of a problem. You have a lidar that is generating the same point, gigabytes per second, or a vision that is generating megabytes per second. You have a problem. So it really depends on the use case, but it has to be things, things that are relevant are imagery on medical devices. Huge problem, right? Because, well, either you deploy something super expensive or you move a lot of data back to the cloud. Smart cities, the same. You cannot, suppose that you want to do parking spaces in the cities, well, you would need to deploy expensive IoT devices all around the parking spaces, which we know how public agencies work and how tight their budgets are. Or you can start to think about, okay, how can I do a little bit more here and transfer a bit there? Automotive, AV vehicles, huge one, real world. Anything you can think that is huge amount of data that you would think conceptually, yeah, I cannot handle it. It doesn't fit in my laptop. So you can synchronize your Fitbit with your laptop or your Apple Watch. That probably is not truly big data.
So when you said images, it actually dawned on me another family of applications would be voice, speech.
Yeah, audio. Yeah. So the way we classify, the ways I mentally classify it, I tend to think in terms of vision and lidar. These are the two examples of today people understand. Then just below that is audio and radar. These are things that are, start to be interesting. Telematics is a bit less. Now it's something around the 50 hertz. GPS data points are normally generated between 1 and 10 hertz. That's borderline to just transfer it, forget about computing it locally. And things like a temperature sensor, a light bulb, right? A smart light bulb that you should just transfer to the cloud, compute, come back.
So are there examples? I suppose there will be examples in things like agriculture, where you have
There are, tons of them. And it's surprising when we started the company, or when we talked last time, things like vehicle to vehicle, right? We found surprisingly that one of the areas where vehicle to vehicle technology, sharing all this information between sensors and devices, tends to be agriculture, because it's a less regulated world than the streets and the cities and the roads. So it's happening a lot that actually they're deploying a lot of sensors locally in the farms with that share not just a point around humidity, but actually pH analysis, full analysis of the ground composition. And you have all these sensors like once every 10 square meters that are sharing data with each other. And then as the machines go by, it's fully adapting to what is happening. Because if you look at something that is hundreds of thousands of hectares, to transfer that data at one every 10 square meters, it becomes a huge amount of data to process.
So, by the way, Bruno, historically, one industry that has dealt a lot with a lot of data for many, many years, even preceding uh, uh, the big data revolution, is oil and gas. So in recent years, they started talking about things like predictive maintenance. So this so in that case, you have some piece of equipment maybe that you're trying to make sure that you catch before it fails. Does that fall under edge computing? Is that some kind of sensor or so? Uh,
I don't know if it's internet connected. Like at the end of edge compute, I think to me it really is. It's not an isolated device, right? If it's an isolated device that works by itself, it's not. There's no cooperation of compute. So I don't actually know how it works for the oil and
I
gas
see.
industry. I know that they're super data rich. I know, for example, that engines in jets, airplanes, they generate a lot of data. As I said, they can generate up to 50,000 points per second. And when they land, they need to transfer a lot of this data out of the airplane. And there is not enough time sometimes to do that. So you end up with this hybrid mode that there is certain elements of the compute that run in disconnected mode, and then when it lands in semi-connected mode. So it's not truly an edge compute, but it's close to it, right? Because it's like a semi-connected modality.
I see. I see. All right. So then we have these edge computing use cases. So people who listen to this podcast are probably familiar with just building machine learning and data applications, right? So that means data ingestion, data pipelines, data cleaning, training, deployment, so on and so forth. So, what of which of these aspects are particularly challenging for edge computing? Is it the data preparation, data cleaning, data ingestion, or is it the modeling or deployment of models, updating models? So they're probably all challenging, you'll tell me. But
Yeah. So
which ones
if
have you spent the most time awake at night worrying about?
yeah, so as you say, all of them have their own twist. Everything that you mentioned has a bit of a problem when you run on the edge. But I would say that there are two things that are uniquely different. One we already talked about, which is the models have to move to an embedded device, and that creates its own set of problems. At the end of the day, basically the issue there is that each system on chip ends up having a number of at the end of the day, machine learning is just matrix operations. So the number of math operators that are available on that chip are going to define how easy or even possible it is to port an architecture locally. So porting and actually deployment of the models onto an actual architecture, it's a big problem, and something that we invested actually a lot of time to make sure that we have pipelines to make it easy and fairly automated. I would say the other one is the actual edge, right? The actual connectivity, that despite doing a lot of processing on the provider edge, you still need to move data to the consumer edge and from the consumer edge to the region. And the data that is being moved, you cannot centralize the data compute. You need to really shard the data compute. And when it's in the physical world, the data is so big that the sharding basically you end up doing by locality, right? The data about San Francisco is only interesting for San Francisco. So we've gone even down and we created a standard with the IETF as part of the location identity separation protocol draft.
Oh, this is with Uber, right? Is that right?
No, Uber is one of the things, right? So we use Uber H3. So what we do is we partition the space into essentially hexagons. these hexagons have different, it's a hierarchical resolution of hexagons. And what we do is for the smallest resolution that we use, which is resolution 12, we assign an IP address, something like an IP address. It's called an EID, which is essentially an IPv6 address. Then when the data being generated, it's assigned to that IP address. It's collated at a bigger, it's basically brokered and aggregated at a bigger level, and that's a resolution 9, which is essentially 0.1 square kilometers, and is multicasted back, broadcasted back to the IP addresses that are moving on the road, right, the vehicles. So that topology, whether it's moving vehicles or it's pedestrians or it's cameras on the street, whatever it is, but that locality of remember, this is the real world, right? So locality is a fantastic sharding key, rather than you would have user ID or time in other type of architectures. For us, localities, and this standard basically allows us not just to shard but also to route the packets the way that the information is traveling. And then each of these shards are essentially a distributed shared memory blackboard. And that's where the inference happens. You get all these annotations from the field, you run a little bit more inference, you do a bit of aggregation, you store it in the right place in the blackboard, and then you propagate it back to the client. That's, at a high level, that's essentially the architecture that we have built to be able to deal with both the high demands of the upload, as well as being able to create this hybrid cooperative compute. So I leverage as much compute as I can from the consumer, and then as much compute as I can from the provider edge. And the rest, once it's cooked, then it goes to the region on AWS.
So when Nexar started, as I recall, you folks were you more like an app on a phone? And then now you have your own devices, your own dash cam, which means you have more control over the hardware, right? So, so edge computing, obviously, for the people who listen to this podcast, are mostly used to cloud computing. So we're talking about, maybe being able to scale out as much CPUs as you need, or renting GPUs that you need. So, but in edge computing, you work with a fixed hardware environment that most of the time you can't change, right?
And actually, once you deploy it, you can change it for a long time. This, on AWS, you can buy an instance and then change your mind and buy another one.
Right.
Here, the hard thing about hardware is that it's hard.
Yeah.
And hard meaning that is difficult and that it doesn't change.
And more slow is dead.
And yeah, exactly. So the decisions that we make, like picking even the system on chip architecture that we have picked for our chips, which is Umbrella.
So by the way, Bruno, before you proceed, what is a layman's very concise definition of system on chip?
Yeah, so if you think about what people call a CPU, right? At the end of the day, the CPU needs to have a cache and needs to have a number of things around it to actually be able to function. So a system on chip is essentially all these things put together so that it actually works, and you can then put it into a board and connect all the different peripherals to it, like the camera and the microphone and whatnot. So what mostly people refer to as CPUs, they happen to be system on chips. It's just that on this world, there is the true core or the true processing unit and the actual system on chip that brings all these caches and memories and buses and layers on top of the system on chip, on top of the core CPU. So you will hear us talk about it. Microcontrollers is the other word that comes frequently, which is even beyond that, right? That it's actually independent. It has its own firmware, its own basically boot loads into a bit of software that is burnt into the hardware, and it just does what it's supposed to do.
So anyone who wants to get serious about edge computing, they really need to know a lot about hardware. Is that the lesson here?
You have to today. Yes, you have to. There's no way to abstract it. So, I mean, all these. Apple does a great job, by the way, with Core ML, for example. I think, in terms of a tool chain to help you work with it is super, super good. But at some point, if you really get serious into bringing bleeding edge networks onto the hardware, you need to start actually understanding how does the neural engine work and how does it not work, even beyond what Apple wants to tell you, because you're trying to do what Neil Gaiman would say, where nobody was before, there were no rules, and now you have to define your own rules.
So 5G, right? So we hear a lot about 5G. So what are the implications for edge computing?
Profound, I think. So, I think I mentioned earlier there are two reasons: low bandwidth, low latency, and high bandwidth. And I think what 5G really brings is a game changer world for both of them, for both low latency applications and super high bandwidth. And the example that I like giving is you could spend $10,000 on a supercomputer architecture that you could put into an autonomous vehicle. And probably you need to spend some of that money anyway, because part of the algorithms that run in the car are mission critical and you cannot depend on any other system. But a lot of the algorithms that run in the car don't need to be in the car. When you think about a data center, right, we used to have 15 years ago servers that were sitting at 3-5% utilization, right? If you remember the Hadoop farms, I mean, I think we might have even talked about it in the past, where you have an average CPU consumption like 5%, so people started to move to ARM architectures and whatnot. So in the car is very much the same, right? You're deploying supercomputer at $10,000, but you only use your card 3% of the time. So what 5G does, it makes feasible to shift a lot of the compute that would otherwise sit idle, compute power that would sit idle in the car, to the provider edge. The second thing that it does is to really be able to move the data, right? So today you have that vehicles are data centers of their own, but they collect a lot of data, but the data sits in the vehicle. It doesn't go anywhere. So from a societal standpoint, forget about anything else. We're not becoming any smarter about how people drive. And the acute issue with driving that we talked about in the past is edge cases. And what 5G is going to make it cheaper to really get exposed to edge cases, which today are being lost. So the 11 trillion miles of driving that humanity does every year are gone to the drain today. 5G is going to make it feasible to harvest a lot of that collective intelligence, crowdsourced vision, like we do, to really gain intelligence around how people drive and how should algorithms truly behave in the field.
So it sounds like, though, that means that there'll be even an exponential growth in the amount of data collected.
Oh, absolutely. I think this, today you can probably see kilobytes per hour or kilobytes per minute, sorry, in terms of actually what's the number? Another company that is building real-time maps, it's collecting around 7 to 10 kilobytes per kilometer. The number that I think we are going to see, it's going to be probably in the gigabytes, if not in the terabytes, of data processed and collected per kilometer. So it's not just an order, it's multiple orders of magnitude. Because the thing is that without that information, and we talked a lot about edge cases in the past, right? We could go on around this for forever if you want, but generalization, the problem with neural networks, and you know about this more than I do, but is that it's essentially is memorization, right? What you end up having is you have more parameters than data points. You just make the network deep enough, and well, bang, it works. But the issue is that driving autonomous vehicles is by definition something that you're biased in terms of data collection. You only train for what you see, and it's a lot that you don't see. And actually, driving is it's a huge long tail. So what we see is that only things like basically leveraging those 11 trillion miles actually can get you somewhere through that crowdsourced vision. We see it, by the way, if you want to go on Captured by Nexar on our Facebook channel, which is what we call PG-13 because we remove real accidents.
Yeah.
But you can see a lot of those edge cases of driving that we post. We help autonomous vehicle companies to use our use cases to create synthetic data that helps them train. But at the end of the day, really, it's becoming a problem that I think only edge will be able to solve, will help to solve to a degree. 5G edge will truly help to bring AI to a new level for not just autonomous vehicles, but medicine that I was talking about earlier, engine diagnosis, things that are truly big data on the field.
By the way, you just brought up a point that reminded me of the following, which is so there's a lot of hype about synthetic data, but two things. One, it might be useful maybe for testing your model for robustness and things like that. So testing. But for training, if, as you point out, Bruno, if you want something really realistic and maybe unusual, you either have to build a simulator so good, right? So that you've spent so much money building the simulator, you might as well just go out there and collect the data. And by the way, it's unclear whether your simulator can even simulate all of the possible edge cases that are out there in the real world anyway. So even if you can, you might be able to simulate a limited number of them. So synthetic data, at least from my perspective, may be useful for testing models here and there, but there's no substitute for real data in many of these applications, right?
You're absolutely right. So I fully agree with you, by the way. I mean, we saw it with all the research that was done with GTA, right? Where you see that it's very good to get to a certain level, and it's very good for debugging. You can do like a 0.1, right? Or a 0.9 if you want, but you cannot do a 1.0 with synthetic data. It's doesn't have the resilience that you need. That's I was mentioning, one of the things that we do is we use our network, which is not as biased. One of the issues with synthetic data is the bias and the data scarcity that goes into modeling the simulator or using synthetic data. And by definition, we're not truly unbiased because people who drive with Nexar today are biased. Eventually, we will be once we are in any vehicle. So there is no bias in terms of whoever buys a dashcam. But it's less biased, right, than what you can get input into a simulator. So we see that these companies that build simulators or that use it for autonomous vehicles, they actually want our data to be able to inform their models. We do ourselves through 3D reconstruction that we provide as for insurance purposes, and the same thing is being used for AV training and validation. One of the things that we do, though, that I think that I would point out in this area in synthetic data is that we really use the outputs of the simulation to help us, of the outputs of the 3D reconstruction to help us understand what are things that we might be missing, right? That you don't know what you don't know. But if you observe the 3D reconstruction out of your field data, it can actually help you. The other reason, by the way, that field data, and you and I talked about it in the past, that that field data is not that. Sorry, synthetic data doesn't work. Is for everything, is that the world is changing, and it's not just changing because there's a new guardrail on the road or there is a new stop, but actually cars continue to evolve. There are new types of cars. Buildings are different. We see, for example, that a model trained in San Francisco doesn't work as well as a model trained in New York. And likewise, right, a model that was trained 15 years ago Now you look at it today, and the city has changed, right? So you can fix some of these to things like domain adaptation, which Trevor Darrow, our chief scientist, has been doing at Berkeley. You can do it through things that we're doing, like self-supervised models. But at the end of the day, there is a limit in that. So to be able to truly leverage you need to do this notion of continuous learning. If you remember my Hadoop Summit keynote years ago, right, on continuous computing. So I'm just basically brought the same thing on the continuous learning. I think we did a talk at Strata years ago, which is the same theory, right? Is only by driving, only by seeing real-time data all the time, only by doing basically these self-supervised methods on a lot of data all the time, you keep basically refreshing the model. And that's the only way, I think, that we're going to succeed in building truly autonomous vehicles and truly any kind of edge intelligence.
By the way, you used the word bias, which gives me an excuse to bring up my next topic, which is this whole umbrella topic of responsible AI, which very roughly speaking means that the teams who build these applications need to consider other things beyond just model accuracy or business metrics, right? So they have to think about privacy, security, fairness. But then now you have edge. So, so edge computing itself may pose certain challenges to responsible AI. Certainly in the case of facial recognition and computer vision. But are there any specific edge computing challenges that may come up in the context of responsible AI?
I think they do a lot, but at the same time, I think the challenges are probably, sorry, let me take that back. I think the challenge is whether you do the edge, the compute on the edge, or the compute on the cloud. I think they're very similar. I think what edge gives you, it's an opportunity, if you're aware, to deal with these things in a better way. And maybe the inspiration for that comes from back to days in advertising, that you look at data clearing houses and DMPs in general, which is company A and company B. They don't trust each other, right? So they go, I have an email, I have a phone, or I have credit records, but I don't want to quite join both pieces of data. And you have this data clearing house that does that join. So the surface, the risk, the exposure of where the data is actually being joined is contained. It's still a problem, but it's a contained problem. And I think one of the things that edge and responsible general machine learning, not just neural networks, have is you can contain the problem to the device where it's being generated, the data, right? So that, like you pointed out, faces and license plates. So things that we do outside of faces and license plates is we analyze the dashboard, we eliminate private elements, we do basically GANs to switch the identity of drivers so that it's impossible anymore to know whether you were driving my car, I was driving my car. So you basically move the problem to the edge so that when data actually makes it to the cloud, the data is truly unidentifiable, anonymous, clear of first and third party, which, by the way, is something that we're doing very aggressively, third-party data, even though, the US, the public roads are public. There's no requirement truly to say I saw Ben on the street and have an image of him, but we're doing it anyway, right? I think Google is doing it. I think we're following European privacy in that sense to basically say we're going to clean it. So really reduce the surface to be as close as possible to where the edge computing is running so that anywhere downstream basically cannot actually look into it. And so it's really a Chinese wall if you think about it, right? There is the personal stuff, and then there is the collective crowd wisdom, shared memory that is not foolproof. That's where ethics have to come into place as a company. But you're trying to contain the problem to a single place.
So something we talked about recently is kind of my fascination with comparing AI and data teams with security teams. So security teams have a longer tradition of anticipating failure and assuming failure will happen. They have incident response playbooks and things like this. Um, AI teams not so much, and ML teams. And but I think maybe Bruno, the answer to this is more hopeful in the context of edge computing, because maybe people who work with edge computing are more paranoid than the traditional ML teams that work on models that get deployed on the cloud. So, uh, what's your sense in terms of edge computing and architecting for failure, resilience, and attacks?
Yeah. So I think you pointed something that I concur with that. With any company that works with real world data at the edge is more subject to scrutiny than other people that might get their data on the cloud because, well, I bought the data from X and now I have it here. And we see that from our customers. They expect us a level of data security, information security, even legal policies that we have around how we deal with data that they would be unheard of on even our investors, right? When they look at Nexar, one of the things they say is like, big brother panopticon type of thing. And we consciously, Aranshir and my co-founder, since the very beginning, is something that we designed the company on purpose in terms of the practices that we do, how do we design applications, how we work, to be aware of it. And things that you were mentioning earlier, like data fusion, right? This one of the things we think continuously, right, is our data by itself might be clean, but what if somebody else would join this with something else? Would it expose other people? The other criteria that I have is I don't want to be in a situation where we are a governmental agency in disguise, right? That the FBI can come in and say, here's a search warrant. Please hand us over all the data. I want to investigate these individuals. So we really took a page from Tim Cook's book when he really said, I'm not going to give a backdoor access to iOS. And we engineered a lot of the encoding and encryption of the identity of the user, identity of the files, the use of ephemeral IDs, authentications in the radius networks. Really, it forces you to contain the problem. As I said earlier, it's a company culture, it's an ethical culture. That you're working with dynamite, so you're actually more careful about it. The problem is that people that have not worked with dynamite and they just use in a mail, they go like, hey, there's no dynamite here. And then suddenly things start to appear. Like when I think it was AOL years and years ago, they disclosed those query logs. And people were able now to reconstruct through differential privacy the identity of individuals that were searching on the logs, just because nobody had thought that would ever be possible. But if it was medical records to start with, nobody would have even thought about doing it, right? Consultation of patients anonymously. It's like, of course you don't do that.
So the other thing that I think is interesting is this notion of failure and assuming that failure is inevitable. And if you do that, then you try to design processes and even tools and systems to minimize the mean time to recovery, right? So that at some point some things will go wrong, but how do I recover as quickly as possible? I assume that edge computing people probably think more about these things than than people who design ML models for the cloud. Because they're always probably paranoid about losing network connectivity. So
Yeah,
that's
yeah.
one. place where failure happens,
That's
right?
it.
Yeah.
So you're aware. It's actually a really good point. I mean, part of the failure is database, like we were talking about earlier, right? Bias, edge, data scarcity. That's part of the silent failures that you don't see. Part of the active failures that you design for, exactly those, is compute, battery, network reachability. So you design around them. You design around caching, about distribution, about, okay, you
Weather.
may exactly right.
Yeah.
So it makes the design of the system surprisingly simpler in a way, because each of the nodes by themselves need to still be functional. So it's like organism in nature, right? You design simple organisms that by themselves work well. When you put them together, you create truly complex systems rather than perhaps complicated systems. And I think one of the things that Edge forces you is to think in terms of these autonomous units that must continue to work regardless of, again, power, heating, weather, network
By the way,
reachability.
weather is a big deal simply even for battery life, right?
Even from a legal, so battery life is it's a surprisingly difficult problem.
Because if it's colder, your battery won't last as long, right? So,
And if it's hot, batteries explode. If they explode, they reduce their charge. And if it's super hot, they're actually dangerous, because if you have an accident with an exploded battery, the battery is more likely to detach itself and go on fire, right? So batteries on IoT devices in general are actually an interesting thing. You want to have a big battery so it can do a lot, but the bigger the battery, the higher the risk.
right.
Again, this goes back to the single node thinking, right? That you think, how do I get a single node to survive, but that is part of an organism when it's connected, it's part of a crowd. And so you're not always thinking like on the cloud that everything's centralized. I can always send, I have access to everything, and I just bounce new servers if things come down. It's like, you don't think about that. When you think on Edge, you have these random failures all the time, that I didn't get my files, they did not get uploaded, the phone is off, the camera didn't switch on, the battery is dead, and you have to design for all of them, because you don't want, to be in a situation that you go like, well, actually, I don't have the data that I'm supposed to have.
So okay, so in closing, this has been a great discussion. I can talk to you forever, but so in closing, Bruno, we're at the start of 2021. So you have such an eclectic background in technology. What are you excited about in terms of technology in 2021? Don't limit yourself to just Edge.
Wow, that's a super tough question. I mean, in terms of AI, I'm super curious into generalized AI. It's like you follow things like the cost of training those super large systems like GPT-3, and that it becomes unaffordable for most people to do it, and you start thinking like, like, is that really the way to go? So, I know we've been looking at it from many places, the generalized AI,
Or even, honestly, even computer vision. There was a paper from MIT where so computer vision happens to be this area where there's enough historical data that you can start modeling the future. So then they started modeling the future in terms of, okay, if we lower error rates in some of these key computer vision benchmarks by this much, how much would it cost? And it's just insane, the cost. you know.
Yeah, so I'm starting to have it's related to the edge, but really the notion of federated learning.
Yeah.
It's beyond edge, but also at the edge, right? It's really becoming super interesting as a concept, that I think we hopefully going to see things advance
Is
in
that
2021.
Bruno? So federated learning is a concept that's a few years old, but a few companies do, notably Google. But as far as I can tell, there's no generally accessible path for people to. There's no TensorFlow for no something, nothing that a regular developer can get their hands on, right?
You could, I mean, there isn't, but there was work done by the team from there, Alex Mola at CMU on the what was called the parameter server, and I think it was on
Right.
GitHub for a while, which was closely related to what Google was doing with the disbelief system.
Right. Right.
So there are bits and bobs on the community that you can get your hands on, but no, you would have to really bake your own
Right.
system.
Right.
The beauty, I mean, the beauty about, again, back to Edge, like I'm a one pony trick at this point. But the beauty of Edge is if you remember back the days of SETI, right, and collective intelligence,
Right.
and
Right.
so I think we're at the point now that something similar really would be super interesting from a federated learning, not just because of the distribution of the compute, but back of some of the responsible ML that we are talking about earlier, right? Is your data doesn't need to leave that place. You can actually just train locally and never get access to it, like
Does
medical data, right?
does Bitcoin mining fall under?
I don't think so. Nothing against Bitcoin mining, but it's a different kind of problem.
Interesting. So what about so you mentioned federated learning. I think the one technology that seems to be more accessible and more people are using is differential privacy.
Yeah, although there is a lot to be done there.
Yeah.
That's an area that
But
is definitely
at
a
least
lot of
there's
research.
more and more tools for developers.
Yeah. It's more accessible in that sense, but I think the gap in terms of how far we are into truly avoiding a network to tell me, hey, I know that you got images from Ben. I think there's quite a way to go there.
But it's increasingly true. So this is something that Ion Stoica and the team behind Ray have been talking about, is that the future of computing will be distributed, right? For a variety of reasons. On just the pure compute side, Moore's law is dead, and there's just no way around. Hardware is getting better, but there's no way you can have that much memory on a single node, right? So, and these models are insanely big for one, right? So,
yeah, that becomes unaffordable, right?
Yeah.
Not just to run, but like just to build these servers and these systems is like we used to have these supercomputers to crack the weather predictions.
And I think actually responsible AI will drive a different class of innovation, right? Force people to do things or add things to their processes and to their tooling.
I think it's a wave, right? We've gone from centralized architectures, distributed architectures, centralized architectures, distributed architecture. So we lived, when Hadoop started to a degree, it was a bit of the distribution. Then we went back to the huge data warehouses again. And now, we've moved all the AI onto essentially a big brain, right? A big cloud or big servers. And what we're going to see is the next wave again to the distributed side will be a few years with the distributed side, and we'll come back to the centralized side. It's been going on for the last 50 years, so I don't think it's going to change.
Yeah. And with that, thank you, Bruno.
Thank you, Ben. It's always a pleasure.